So the purpose of the telescope, it's a follow-on to Hubble, and Hubble has been around for more than 30 years. It's brought us amazing science and images of our great universe. Webb is 100 times more powerful, if you could imagine that. So it's going to allow us to see deeper into the universe, further back, a lot clearer, because we have infrared, so we can see through the smoke and gook of space. So it's going to show us the early formation of early stars, early galaxies, and the 1, 2, 300 million years after the Big Bang.
For centuries, humanity has looked to the stars, hoping to uncover the secrets of our origin. But now, the James Webb Space Telescope, the most powerful instrument ever built, has returned with something else entirely. Impossible galaxies, bizarre cosmic structures, signals from nowhere. This isn't just a discovery, it's a wake-up call. Because what Webb just revealed might not only rewrite the laws of physics, it could awaken something far more terrifying. It all began with a deep gaze into ancient light. There, Webb spotted MOMZ-14, the most distant galaxy ever recorded, 13.53 billion light-years away, formed just 280 million years after the Big Bang. But this wasn't just a distant blur. MOMZ-14 was mature, organized, and chemically evolved in ways that contradicted every model we've ever trusted. Its star-forming rate is rapid, and its compact structure suggests it underwent a highly efficient early evolution, something our simulations didn't predict. Scientists initially suspected a calibration error, but repeated measurements confirmed its age and characteristics, leaving astronomers with more questions than answers. How could such a well-structured system form in a universe still crawling out of its infancy? Even more astonishing was the galaxy's compact yet highly efficient star formation. MOMZ-14 was producing new stars at a furious pace, rivaling much older galaxies, while maintaining a surprisingly stable, ordered structure. Its rotation hinted at the early formation of a disk-like shape, challenging the idea that such organized dynamics needed billions of years to develop. The presence of dust, fragile grains that should have been destroyed by intense radiation at this time, only added to the mystery, indicating rapid dust creation and survival mechanisms previously unaccounted for. These puzzling characteristics hinted that the processes shaping the earliest galaxies were far more complex and accelerated than our current simulations could capture. Recent spectroscopic studies of MOMZ-14 have also revealed an unexpectedly high ratio of ionized oxygen in its interstellar medium, a sign of intense radiation from massive young stars. According to research published in Nature Astronomy, this elevated ionization indicates that MOMZ-14 contributed significantly to the reionization of the early universe, a pivotal era when the first galaxies transformed the surrounding hydrogen gas from opaque to transparent. This discovery not only highlights MOMZ-14's role as a key player in cosmic evolution, but also provides valuable insight into how such early galaxies influence their environment, accelerating the transition from the cosmic dark ages to the bright star-filled universe we observe today. The discovery didn't just raise eyebrows, it triggered a quiet panic in cosmological circles. Could our understanding of the early universe be fundamentally flawed? And just when scientists began searching for answers, the telescope delivered something even stranger, a cosmic enigma that defied explanation, challenging the very fabric of cosmic history and forcing a radical rethink of galaxy formation theories. Next came the observation of JWST 13-1, another early galaxy glowing in defiance of cosmic expectations. At 330 million years post-Big Bang, the universe should have still been drowned in neutral hydrogen, blocking light. Yet this galaxy's emissions came through clear and strong. That hydrogen fog, thought to last hundreds of millions of years, was apparently parting much sooner. The galaxy even showed evidence of ionized gas regions, as if it had already begun influencing its environment. And the implications? Either ionization happened much earlier than we thought, or the cosmic fog lifted for reasons we don't yet understand. This discovery challenges our timeline of how and when light first broke through the cosmic darkness. These weren't just unusual blips. They were signs of a universe that was evolving faster and perhaps smarter than our textbooks allow. And then came the whisper, not from a galaxy, but a planet, K2-18b, a Hycean world 124 light-years away. In its atmosphere, JWST detected dimethyl sulfide, DMS, a molecule we've only ever seen produced by life on Earth. Microbial, oceanic life. K2-18b orbits a cool dwarf star and likely possesses a thick atmosphere and liquid water oceans beneath its hydrogen-rich sky. Ideal conditions for microbial ecosystems. While far from confirmation of alien biology, it was enough to shift the conversation. Scientists were no longer debating whether life could exist elsewhere. They were now seriously examining where it might already be. The sheer possibility of biogenic molecules outside Earth shakes the foundation of our solitude in the universe. This discovery also highlights JWST's unprecedented ability to examine exoplanet atmospheres with remarkable sensitivity, opening a new era of astrobiology. By detecting trace gases like DMS, JWST provides clues about chemical processes that could indicate life even on worlds vastly different from Earth. These findings drive a surge in targeted observations of similar Hycean and ocean worlds, expanding the search for life to diverse planetary environments and redefining criteria for habitability beyond the traditional Earth-centric model. And as our focus returned to galaxies, JWST showed us something even more unsettling. Imagine a perfectly formed spiral galaxy, twisting arms, massive core, immense gravity. Now place it just 2 billion years after the Big Bang. That's the Big Wheel Galaxy, an entity that by all rights shouldn't exist yet. Most early galaxies were thought to be irregular, clumpy, and turbulent, but the Big Wheel is massive, structured, and rotating like it's had eons to evolve. It's 5 times more massive than the Milky Way and teeming with mature stars. This galaxy isn't just early, it's sophisticated, and its existence implies that massive structured galaxies were already forming when the universe should have still been in chaos. It suggests that large-scale cosmic order arose long before we imagined. Its well-defined spiral arms and dense core challenge current models of galaxy formation, which struggle to explain such rapid organization in a young universe. The Big Wheel forces scientists to reconsider the speed and mechanisms of matter assembly, star formation, and gravitational dynamics. This remarkable find pushes the boundaries of cosmology and hints at unknown processes accelerating cosmic evolution, rewriting the timeline of how the universe transitioned from chaos to order. The message was becoming clear that the universe didn't wait around, and neither did its secrets. The James Webb Space Telescope, JWST, has taken monumental steps toward uncovering evidence of population 3 stars, the universe's very first generation of stars, formed from pristine hydrogen and helium shortly after the Big Bang. While directly observing these ancient, massive, and metal-free stars remains challenging due to their extreme distance and faintness, JWST's advanced infrared instruments have detected compelling indirect signatures. Notably, astronomers analyzing JWST data from distant galaxies like GNZ11 found regions of ionized helium gas with no heavier elements, a hallmark of radiation from population 3 stars. Additionally, JWST observations revealed galaxies containing unusually hot and massive stars whose intense ultraviolet light hints at stellar populations resembling the early universe's first stars. These findings mark a breakthrough in studying cosmic dawn, offering critical clues about how the earliest stars ignited, influenced galaxy formation, and enriched the cosmos with the first heavy elements. As JWST continues to peer deeper into the cosmos, it promises to shed even more light on these elusive pioneers of the universe. Not everything James Webb sees is distant. Some of it is dangerously close. The James Webb Space Telescope recently spotted something alarming. Asteroid 2024 YR4, a 200-foot wide chunk of rock hurtling through space on a path uncomfortably close to home. Earth, thankfully, is no longer in danger. But the moon? That's still uncertain. Its trajectory brushes past us with what astronomers call a close shave, just missing Earth by a margin that's razor thin on a cosmic scale. What's even more startling is how suddenly it appeared, bypassing traditional detection systems before being flagged by JWST's powerful infrared vision. This moment was a wake-up call. So, James Webb isn't just peering into the distant past, it's also standing guard over our future. Its unmatched ability to detect, track, and analyze fast-moving objects like YR4 gives scientists the crucial lead time needed for early warnings. And as the telescope stayed locked onto the near-Earth neighborhood, it began to notice other things no one ever expected to see. Gravitational lensing is beautiful, yes, but rarely perfect. Yet James Webb captured an Einstein ring so precise, so mathematically exact, it bordered on art. Light bent into a seamless circle around Galaxy J418. The symmetry stunned astrophysicists and hinted at deeper rules in how matter interacts with space-time. For such symmetry to exist, the alignment must be flawless, within fractions of a degree across billions of light years. The odds are staggering. Some believe this could be evidence of geometric constants embedded within the cosmos. Coincidence? Maybe. But as the perfect curves stared back, it began to feel like the universe was drawing blueprints, not chaos. And the telescope kept following the patterns. In a part of space with no visible stars, no galaxies, and no black holes, JWST detected a gravitational lensing effect. This shouldn't happen, not without mass, but the lensing was clear. Light from background galaxies was bending, distorted by something unseen. Some say it's dark matter, but the shape was too focused, the curve too deliberate. This didn't behave like a mist. It behaved like a hidden object. The lensing pattern suggested edges, symmetry, and concentrated mass, all unusual for typical dark matter distributions. What's out there, bending light without showing itself? Or a relic from an ancient event? The mystery deepens, and scientists are more concerned than ever before. Across a billion light-year stretch, James Webb Telescope mapped something that looked less like randomness and more like architecture. An intergalactic filament, galaxies arranged like clockwork, redshifts that ripple like measured waves. The structure's density and the distance between galaxies followed repeating patterns, a spatial rhythm. Gravity can do amazing things. It pulls stars and galaxies together and shapes the universe. But can it create a perfect pattern? Can it form symmetry that stretches across billions of light years? The cosmic web is already a fascinating structure, but this level of order feels almost deliberate. Some scientists say it's just natural alignment. Others believe it might be something more, something intentional. The way galaxies are spaced and lined up doesn't look random. It looks designed, almost like a giant circuit board or musical notes perfectly arranged across space. Could this be a sign of something greater? Maybe even proof of a hidden intelligence built into the fabric of the universe? In a stunning revelation from late 2024, the James Webb Space Telescope uncovered a trio of massive, dust-shrouded galaxies, nicknamed the Red Monsters, that existed more than 12.8 billion years ago. These galaxies are extraordinary not only for their sheer size, each containing roughly 100 billion solar masses, comparable to the Milky Way, but also for their dusty nature, which had previously made such ancient giants difficult to detect. What makes the Red Monsters remarkable is their surprising maturity. Despite their youth, They already show complex structures and heavy dust enrichment, suggesting that star formation and chemical evolution began much earlier than expected. This challenges the view of early galaxies as simple, chaotic systems, and reveals a more advanced level of organization in the young universe. The dust within these galaxies also tells a fascinating story. Dust forms from heavier elements produced in the hearts of stars and spread by supernovae, so its presence indicates that multiple generations of stars had already formed and died, enriching these galaxies early on. This challenges earlier assumptions that the early universe was largely dust-free, and that dust production took much longer to accumulate. The discovery of the red monsters forces astronomers to rethink how the earliest galaxies assembled. It suggests that, under certain conditions, massive galaxies could form surprisingly quickly and efficiently, possibly aided by factors like intense gas inflows, early mergers, or even the influence of supermassive black holes. The James Webb Space Telescope was built to peel back the layers of time. Instead, it might have revealed something far deeper: that we are part of a cosmos not just ancient, but deliberate. Galaxies that defy age, planets that whisper life, rings too perfect to be random, signals too rhythmic to be chance. And if JWST has shown us anything, it's that we've only just begun to see. So now we ask you, are these signs of design, echoes of memory, or the first steps toward understanding something far older and far stranger than we ever imagined? Drop your thoughts below. Like and subscribe if you want to stay one step ahead of the cosmic curve. Because the next image from Webb, it might not show us where we came from, but where we're meant to go.